Most trigonometry students find the idea of writing proofs to be very scary and intimidating, but I have some really good news for you. You actually already have most of the skills that you need to be able to do these proofs. The difference between what we did in the last topic, simplifying a trigonometric expression, and proving a trigonometric identity, there are two basic differences. One is that the proof is a little bit more formal, but the body of it is pretty much still the same as what we did in the last topic. And the second is that instead of simplifying to an answer that you have to figure out for yourself, you're actually already given the answer. Here's what I mean. Let's say that we were asked to simplify this trigonometric expression. I might start by putting it all in terms of sines and cosines. I'm going to rewrite the expression I started with. I've just rewritten it here, and then underneath that I'm going to rewrite it again, but I'm going to make one change. And that is to write secant as 1 over cosine. In the next line, I'm going to find a common denominator and apply it. So whether you write that times cosine over cosine or not, the next step is to write cosine times 1 over cosine minus cosine squared over cosine. And once you have it in that form, you've now got a common denominator, so I can rewrite it again. Notice that each time I write a new line, I'm just copying the line above, making one or sometimes two changes at a time. This is how you get your reader to follow you from one line to the next. You don't necessarily have to highlight that this is the thing you changed. It's pretty obvious the things that you didn't change, and the things that you did change then stand out. All right, let's keep going here. I now have a common denominator, so I've added my fractions together. I'm going to rewrite it again. This time I'm using the identity sine squared equals 1 minus cosine squared. I'm going to rewrite 1 minus cosine squared as sine squared. In this step, I can now see that I can cancel these two, and I'm left with just sine squared of theta. That's how we did simplifying. Simplifying a trigonometric expression involved these steps. See or copy the original expression and change one thing at a time until you had something else, something simpler. Now I'm going to change this so that instead of simplify a trigonometric expression, the assignment is to prove, so I'm going to change this here, it's going to now say prove cosine times the quantity secant minus cosecant equals sine squared of theta. And that's the difference. All of the work that I need to do this problem is exactly the same as what I did the first time. I do need to add a couple of things to turn this into a proof of this identity up here. And those involve indicating to the reader that I've started in a particular place and I've ended with the answer. So, for example, I might write left-hand side equals, this is the left-hand side of my identity, right? This is the left-hand side of the thing that I'm trying to prove. It's only the left-hand side. There's no equals here. The equals is on this side because I'm indicating, this is like a bookmark to the reader to say, look here, this is where I'm starting, the left-hand side. The left-hand side is equal to this. This is what I was given. In writing this first step, I have not made any changes to my expression. I have simply copied it down. So when you're writing a proof, the first thing you want to do is write left-hand side equals and copy out the left-hand side. After that, you're going to need to indicate that each line was equal to the one above it. This line is equal to this line. Because in order to get from this line to this line, I changed one element of the line above into something new. Then the next line is equal to that one, and the next one, and the next one. all the way down to the end. The other nice thing about this, as I mentioned a minute ago, is that you have the answer. You're no longer trying to simplify into something that you're kind of hoping is the right answer. You know what the answer is supposed to be. You're trying to prove that this is an identity. And so you know you want the left-hand side to look eventually like the right-hand side. My last step here is going to be to write equals right-hand side. Now, in a lot of cases, this isn't strictly necessary, right? You don't have to write left-hand side and right-hand side, but I like to see those because I want to see your thinking process about how you're starting this and to know that you know where you're going. So I would like you to write left-hand side equals, copy out the left-hand side, and when you're done, there's your answer, there's your right-hand side. I want to see you write equals right-hand side. Normally, I am not a my way or the highway kind of teacher, but with proofs, because they are so intimidating, I want to give you a platform, a template, basically, on which you can hang all of your proofs. The format will be the same every time. You'll start with left-hand side equals, you'll copy out the left-hand side. At the end, you'll say equals right-hand side. And in between, all of this stuff in here, well, that's all what we did in the previous video. We know how to do that part. Now, there are a couple of modifications I will allow, and one of them is that you can start with the right-hand side equals and then go from there. And when you get to the left-hand side, because that's what you would be doing in that case, you would write equals left-hand side. Sometimes the left-hand side is easier to start with, and sometimes the right-hand side is easier to start with. So you can do it in either direction as long as you start by telling me where you're starting and end by telling me where you're ending. The trick in knowing which way to start is actually kind of ironically that you probably want to start with the more complicated looking side. And the reason for that is that there's more room to play around with this. I can change cosine into 1 over secant. I can change secant into 1 over cosine. I can change cosine into the square root of 1 minus sine squared. There's a lot more room to play here than there is with just sine or sine squared. So a good rule of thumb is to start with whatever side is more complicated looking. Write that side is equal to, and copy it out, do your work, and then write that it's equal to the other side. All right, so that's the structure I want to see. Let's do another example. This time, I'm asked to prove that the tangent squared of x minus the cotangent squared of x is equal to the secant squared of x minus the cosecant squared of x. Well, both sides look equally kind of complex, if you ask me, so I think I'm just going to stick with the left-hand side. To prove this, I'm going to write left-hand side equals. Then I'm going to copy the left-hand side exactly as it is. I'm not making any changes yet. I'm just copying it out. Now, I know that tangent is sine, tangent squared. Tangent is sine over cosine, so tangent squared is sine squared over cosine squared. And cotangent is cosine over sine, so cotangent squared is cosine squared over sine squared. I've made one change to this expression. Well, I've made two, but it's the same change for both terms. So now this thing looks like this thing. Notice that the equal sign is directly under the original equal sign for my problem. Now I have two fractions, so I think I probably want to try and find a common denominator. I'm going to multiply this term by cosine squared over cosine squared, and this term, let's see, how should I do this? I don't want to lose that equal sign altogether, but I'm going to try to squeeze in a sine squared over sine squared. Then I'll put my equal sign back in there. That means that I have the sine to the power of 4 of x over sine squared cosine squared minus cosine to the power of 4 of x over the same denominator. That gives me the sine to the fourth of x minus cosine to the fourth of x all over sine squared x cosine squared x. Now, at this point, it's not really clear where to go. I don't know what the sine to the fourth minus the cosine to the fourth is. I could change sine to the fourth to sine squared squared, and cosine to the fourth is cosine squared squared, and then I'd have a difference of squares. I think that might be the way to go. But it's not obvious, and sometimes it's not. Sometimes you have to play around with stuff, maybe off to the side, maybe on some scratch paper, but it won't always be obvious what the next step is, so you just kind of have to play around with it. Let's say for the moment that I want to play around with the idea that sine to the fourth of x is equal to the sine squared of x squared, and cosine to the fourth is the cosine squared squared. That means I could rewrite this as sine squared of x squared minus cosine squared of x squared all over sine squared of x cosine squared of x. Well, now I have a difference of squares. I have a squared minus b squared, and that's a plus b times a minus b. That's all still going to be over my common denominator. Now I'm going to notice that I have a sine squared plus cosine squared here, which is 1. So my next step is going to be to say that that last step is equal to sine squared of x minus cosine squared of x all over sine squared of x times cosine squared of x. It's still not super clear where to go, but I have a fraction that has a minus in the numerator. So that means I can write this as two separate fractions if I want to. That line is equal to the sine squared of x over sine squared of x cosine squared of x minus cosine squared of x over sine squared of x cosine squared of x. Now I can do some canceling. For example, sine squared cancels with sine squared in that term, and cosine squared cancels with cosine squared in that term. That leaves me with that line being equal to 1 over the cosine squared of x minus 1 over the sine squared of x. And I know my reciprocal identities, so I can write this as secant squared of x minus cosecant squared of x. And all of a sudden, this thing that I started with, tan squared minus cotan squared, looks like the right-hand side, secant squared minus cosecant squared. So I'm done, but I need to indicate to the reader that I'm done. So I'm going to write that that last line equals the right-hand side of my identity. The left-hand side, tangent squared minus cotangent squared, is equal to this, which is equal to this, which is in turn equal to the next line. That's equal to the next line, and that's equal to the next line, which is equal to the next, and the next, and the next line. And all of that is equal to the last line, which is equal to the right-hand side. Therefore, the left-hand side is equal to the right-hand side. The left-hand side is equal to the right-hand side. So I have finished my proof. It is actually really very normal when you're learning how to do this to start and get stuck and have to start over. You might get to this step and do something different in this step, or you might take a completely different approach. The thing is to keep trying and keep practicing. Because this is such a challenging task for so many students, I'm just going to do several more examples in this video. Each one will be a different identity, and sometimes we might start on the left-hand side or the right-hand side, but I'm just going to work through several examples so that you can see kind of what my thought process looks like. The instructions for this one say verify the identity, and the identity they want us to prove is here. Verify the identity means verify that it is an identity. In other words, prove that this equation is true for all values of theta. So this time, the left-hand side looks considerably more complex than the right-hand side. So I'm definitely going to be starting with the left-hand side. So I write left-hand side, or LHS, is equal to, and then I'm going to copy out the left-hand side. I'm not making any changes. I'm not taking first steps. I'm not doing anything at all. I'm not simplifying anything. I am literally just copying it out. But I'm not copying out the right-hand side because that's what I'm trying to show that this is equal to. If that left-hand side is equal to that, what is that equal to? Well, there are several things that I can do. I can simplify tangent. I can simplify secant. So let's do that. I think a good strategy is often to try to get anything that's not a sine or a cosine into those two ratios. So let's rewrite this as 2 plus, I'm going to write tangent as sine over cosine, but it's tangent squared, so it's sine squared over cosine squared. Secant is 1 over cosine, so secant squared is 1 over cosine squared. Now I have a complex fraction. So for my next line, I feel like I have two options here. One is that I could try to simplify this complex fraction. The other is that I could change this into a fraction so I had a common denominator. But my denominator would need to be 1 over cosine squared. That feels kind of messy to me. So I think I'll go with my first reaction, and that is to try to simplify this fraction a little bit. I can write this as 2 plus sine squared of theta over cosine squared of theta, all of that, times cosine squared of theta over 1. In other words, since I'm dividing the numerator by the denominator, and the denominator is a fraction, I can write that denominator as the reciprocal and multiply. Well, now when I distribute, I'm going to get some things to cancel here, but I'm going to be multiplying 2 by the cosine squared as well. Oh, I left off my minus 1. That's a really easy mistake to make. This line here is not equal to this line here unless I include every piece in one form or another, and that includes that minus 1 there. All right, let's do our distribution. 2 times the cosine squared over 1 is just 2 times the cosine squared. And then I have sine squared over cosine squared times cosine squared. So the cosine squareds are going to cancel out, and I'm left then just with sine squared of theta. And then I have my minus 1. Now I have an expression that has cosine squareds and sine squareds in it. And it might be possible to combine these if they're both either sines or cosines. So let's think about, maybe I'll change the sign. Let's think about rewriting sine squared as 1 minus cosine squared. That means that line above there is equal to 2 times the cosine squared of theta plus sine squared can be written as 1 minus cosine squared. And then I have my minus 1. Now I'm going to try to get rid of these parentheses. And since I'm adding sine squared, I'm adding 1 minus cosine squared, I can basically just drop the parentheses. So I get 2 cosine squared theta plus 1 minus cosine squared theta minus 1. The 1's cancel, and I have 2 cosine squared theta minus 1 cosine squared theta. That's cosine squared theta. And lo and behold, that's the right-hand side. I need to move my cosine squared over because I didn't leave room for an equal sign, so I'm just going to rewrite that line. The line before was equal to cosine squared of theta, and that in turn is equal to the right-hand side of the equation I was given, the identity they asked me to prove. So I'm done. I've proved this identity. Is that the only way I could have done it? No, not at all. In fact, I don't know if you remember, but way back up at this step here, I was considering getting a common denominator first, combining these two bigger fractions, and then going on from there. And I could have done that. That's completely legitimate. I just happen to have done it this way. This isn't the only substitution I could have made. Down here, instead of sine squared equals 1 minus cosine squared, I could have said cosine squared is 1 minus sine squared, and put parentheses around that and carried on from there. Ultimately, I would have ended up with the same thing. Notice that my process is the same though. Left-hand side equals, copy out the left-hand side. There's going to be a bunch of stuff in here, and then equals right-hand side. So this piece in here, let me highlight it. This piece in here, all of that work, is what we did in the previous topic. All we've done here is simplified this. Actually, I need to include a little more here. I need to include the first line there. What we did in the previous topic is we learned how to take a trigonometric expression and simplify it. And that's what we've done here, except I know the answer. I've also added left-hand side equals and equals right-hand side to the process. And very importantly, I've made sure that all these equal signs line up. It makes for easier reading. Okay, let's try another one. This time we've been asked to verify the identity 1 equals 1 minus the cosine squared times 1 plus the cotangent squared of t. I'd like to point something out here. It might be tempting to divide both sides of this equation by, for example, 1 minus the cosine squared. While that's legitimate algebraically, 1 minus. I'm not allowed to do that here because this only works if this equation is true to begin with, and we don't know that it is. We're trying to prove that it's true, so I can't use the fact that it's true in trying to prove that it's true. That's circular logic. So I have to pick one side or the other and manipulate it until it looks like the other side. So let's erase this. Do not manipulate both sides of the equation when you're doing a proof. What I can do is pick a side, and this time I'm going to use the right-hand side because it's much more complex looking than the left-hand side. And I'm going to rewrite it. Once I've rewritten it, I'll take a look at all the different things that I have in it and decide which ones I want to change. For example, I have a cosine here, but I have a cotangent here. And cotangent is neither sine nor cosine. So let's change it into sines and cosines. That first line is equal to the same first factor, no change there at the moment, times 1 plus, well, remember that cotangent can be thought of as cosine over sine. I've done this a couple of times now, so off to the side here, I'm just going to do a really quick review. The reason that I can get away with just doing the squared thing there is that cotangent of theta is really just cotangent squared is really just cotangent of theta all squared. And that means that since cotangent is cosine over sine, now when I redistribute my exponent, I get cosine squared over sine squared. So whenever I do that, like tangent is sine over cosine, and I just go ahead and I stick the squareds on there, it's because I'm thinking about cotangent squared as cotangent of theta all squared. And then when I do the substitution, I'm doing it inside the parentheses and then squaring the result. So that's how I get away with that. All right, now I have all sines and cosines, but I also have a fraction here, and I have 1 minus cosine squared here, which I could change to sine squared. I don't know if that's really what I want to do. In fact, let me do this. I'll leave that off for now. I'll rewrite my second step, or my next step. I'll leave 1 minus cosine squared for now. And I'll write my second factor here so that I have a common denominator. 1 can be thought of as sine squared over sine squared. So I'll rewrite my second factor as sine squared over sine squared. plus cosine squared over sine squared. Therefore, they have a common denominator of sine squared. So I've taken this expression and in the next line rewritten it as this expression. That's the whole point. One line at a time, taking one thing and changing it into something else. All right, now I recognize that sine squared plus cosine squared is 1. So I can rewrite my expression again, but I have to write the whole thing. I still have 1 minus cosine squared of x, sorry, it's t, times 1 over the sine squared of t. I have to write the equals, I have to write the factor that I haven't changed, and then I write the factor that I have changed. Don't just write down the factor that you're changing, because otherwise it's not true that they're equal. All right, now I can see that I've got a sine squared in the denominator here. Ideally, I'd like to cancel that with something, and if I change this, then I can do that. 1 minus cosine squared is equal to sine squared. So now I can cancel those, and there's nothing left. So my answer is 1. Importantly, though, my answer is 1, which is my left-hand side. So I need to write this last line as well. Now again, this isn't the only way necessarily that I might have done this proof. You may or may not remember that back in this step here, I was considering changing this to sine squared. I didn't because I didn't know quite how this is going to look when I got that next step or the next again step. If I had, in some cases, it might not have proved to be very beneficial and I might have to have changed it back. There's nothing wrong with that if that's how it happens. But I decided to leave it until I knew what this factor was going to look like, so I would know what I was working with and what I needed to change this one into. For the last example I'm going to do on this video, I'm going to write out the entire proof first. And then I'll walk through it with you and explain why I did the things that I did. But more importantly, I want you to see what it looks like to read a proof that's been written, a completed proof. There are some of these in your textbook, but it's kind of hard to talk about those since we're not actually meeting in person. So let me do that. I'll set up the next screen for you, and then we'll talk about what it is I've written. Okay, here's my proof. The left-hand side is just copied out. In fact, I literally copied and pasted it down here. This can be changed to this, which can be changed to this, to this, to this, and so on. I've left it blank here on purpose. I'll come back and explain why I did that in a minute. So can you follow this proof? Can you see what I did between the original and the next line? Well, clearly this factor is the same. So the changes I made are in this factor. Cotangent is cosine over sine, and cosecant is 1 over sine. Once I had it in that form, I noticed that they had a common denominator. So can you see what I did next? Again, this factor hasn't changed. So the factor that's changed is this one, and all I've done is combine. I already had a common denominator this time. Combine the numerators. All right, so what do you think I did next? I treated this factor like it was over 1, and I multiplied my two fractions. I had this numerator times this numerator over this denominator times 1, and that gave me this. What about the next step? Is it obvious? Cosine minus 1 times cosine plus 1 is the difference of squares. If you weren't sure and you just wanted to distribute that, you could have done FOIL, you could have done distribution. You might have had another step in here where you had to cancel middle terms, but you could have ended up here as well. In fact, you would have at some point. Now that it's in this form, can you see what I did next? How did I get from cosine squared plus 1 to negative sine squared? It's harder to see that one, isn't it? Well, I know that 1 minus cosine squared equals sine squared, but this is cosine squared minus 1. So I use the fact that negative 1 minus cosine squared is equal to negative sine squared, and then I distributed my negative. I got negative 1 plus cosine squared of theta equals negative sine squared. And then I reverse these two terms, cosine squared minus 1. equals negative sine squared. So I used this idea from algebra that negative a minus b equals b minus a. What I had here was a b minus a. So I changed it into a negative, can't even find it now, negative a minus b. I kind of did that backwards. But the result is that I ended up with the top of this thing here being equal to negative sine squared. Now, I've done this on purpose. I left a blank space here, and I took a big step here. And the fact that I've had to explain how I did that step means that I need to fill in the blank. There's not enough information from this step to this step. I'm not going to be in the same room as you when you read my proofs, right? So I can't stop and say, well, how did I get from here to here, and explain how I did that. I need to have a step, or perhaps more, in here that explains how I got there. So let me fill that in now. So in this step that I included, this intermediate step that I included here, all I've done was indicate that what I'm doing is taking cosine squared minus 1 and reversing the order. I'm using that little rule that I had down here. I've erased that one now too. That is perfectly acceptable to assume that another mathematician knows. So the fact that I've got b minus a here and negative a minus b here, I can make that jump. That's a lot clearer how I got from here to here, and then from here to here is less of a big step as well. You might not remember that 1 minus cosine squared is sine squared, but it's a lot easier to look that up than if I had to jump from this step to this step. You know how when you're reading a textbook and you just don't quite get how the author got from line 1 to line 2 or line 7 to line 8, or when you're watching another lecturer on YouTube and you can't quite figure out how they made that particular step? Well, that's what we're trying to avoid in writing proofs. You can't necessarily write every single little detail because then the thing would be pages and pages long. But equally, you don't want to leave too much out either. Now, I can usually fill in the gaps, but I'm not trying to get you to impress me with how little you can write. I'm trying to get you to be able to write a proof that another student or another mathematician would understand without necessarily being able to ask you questions about it. At this level, it's probably not going to be very difficult for another mathematician to fill in the blanks. But this is the first sort of baby step in learning how to write proofs. So figure out how to do it well now. Keep using that practice as you go forward. Yes, you may have to write more now, but trust me, in the big picture, you're going to end up having to write less and explain less if you just take the time to make sure you include enough steps. One of the examples in your textbooks is going to show you how to prove an identity by working with both sides separately. I don't want you to do it that way. You're welcome to look at that strategy, see what it involves, and it's effectively what we've been doing. In fact, you can use that strategy, but when you write it down for me, rather than starting with the left-hand side and getting it to an expression, and then starting over with the right-hand side and getting it to an expression, instead of leaving it like that, do your work backwards so that your left-hand side comes to being that expression and that your right-hand side follows on from that instead. So you can use that as a beginning point, but please still write your work out for proof so that you start either with the left-hand side, work all the way through until it looks like the right-hand side. So I'm not going to do an example like that because I don't really want you to use that strategy as a go-to, at least not for now. The last example in your textbook is called Trigonometric substitution, and I'm not going to do an example like that one either, primarily because this is a valuable skill that doesn't really belong here. We're not proving an identity, we're doing a substitution and a simplification. Not only that, but it's not really something that you need for this course. When you do need it, it's pretty easy to pick it up, so I'm going to leave that one off here too. Now, we've done several proofs, but there's actually an infinite number more that we could do. So I'm going to leave it there for this video. And if time allows, I'll make another video with some more examples. But for now, I think it's time we moved on to the next topic.